is to see how this development that we did is equivalent for the MIT rule. So what I did, I used the same structure of the controller that we have used for input-output. So basically it's a feed-forward controller with a data gain. And then, but we formulated this in a state space model. And from the state space model, we were able to find using the lyapunov, what will be the update rate for the parameter that you need to put in the controller. Now, the first thing that we have to know is that the lyapunov equation not only is function of the state, but it's also function of the parameters that you don't know, that you are trying to attack. Right? This is the way we construct it. So if you look to any lyapunov function that is not adaptive, you will not find these parameters here. Right? Then by deriving v prime with the lyapunov function and requesting that the lyapunov function derivative has to be negative, we were able to select one possible solution, not all possible solutions, one possible solution that dictates that the derivative of theta with respect to time is equal to minus gamma times the reference signal, times v transpose, times p times the state errors. Right? Now the question is the difference between this and the previous result. This one is function of the state. We have here state appearing here, so it's state feedback.
So I don't think we did this.
Sorry?
I don't think we did this. This part we did not do.
This part we did not do?
Yeah.
No, sir.
But we did something similar in the single input, single output.
We talked generally about.
You talk generally about the lyapunov theory.
But you want us to do this?
Yes.
Yes.
I think I did it, but maybe I did it myself. Right. So basically, this is what it is. We have to look to lyapunov. So lyapunov is equal to half xe multiplied by b multiplied by xe transpose multiplied by e plus theta t squared. I'm going to call all this as theta t, this term, right? And we are going to put 1 over gamma here as a factor that will allow me to balance between the state error and the convergence for the parameter theta. So this is just one parameter gamma that will help me to put more emphasis on the lyapunov in which one I would like to minimize, because my point is to make v minimum. Right? Then from there, of course, this function now is function of x and theta, just to be rigorous. So this function would be 0 if the error and theta is 0, both of them. So theta t. So which means that your error is 0 and your parameter converges to the exact parameter that you have. Theta equal to theta 0.
But here, so what is XE?
XE is the error. Is the error between the system. That's a good question. So basically we did the x prime is equal to a multiplied by x plus b multiplied by u. And then we have xm prime, my reference model, is equal to am xm plus b, what we call it, bm, not bm, times the reference. Let's say bm. That's the difference between b and bm is just the gain theta, right? And then we selected b as equal, u as equal to theta multiplied by the reference, right? So this is your u that you have here. So what we are going to do if we make the difference between the two, so we extract the error dynamic between the two. Error dynamic, we have x prime minus xm prime is equal to, we are using the same m, right? Not different m, because we are using only feed-forward controller, so the same m in both. So we will have a multiplied by xe plus b multiplied by theta minus bm, the whole thing multiplied by the reference. Right, so this is how we constructed the
U reference.
sorry?
U reference?
The U reference or reference. Huh? U reference.
Total x dot m. Why a not am? Because here.
Because we are assuming the problem is only here.
Yeah. So it's
For this problem.
Yeah, for this one.
For this problem.
Yeah, so
Yeah.
the same A system.
The feed forward. The same system as before. Right? So we are using the same, the issue is only between B and BM. BM is in fact equal to theta 0, theta naught, something that I don't know, multiplied by B. This is what I'm assuming here. But the value of B, the gain in B, I don't know. So this is what I'm putting here. So basically when we write this dynamic, we are able to write it as x prime minus xm prime is equal to a multiplied by, this is of course x e dot. This will be equal to a times xe plus b multiplied by theta minus theta 0, the whole thing multiplied by u reference or reference to b1. So this is my model. This is the dynamic of the earth. So there is a similarity between what we did input-output and what we did here. In the input-output, we start with the transfer function, but we computed y minus ym, which is the output level. Here we are not looking to the output level, we are looking to the state level. So this is the dynamic that I get here. The same dynamic that we have between these two. You are okay with this? All right? So if you go back now to our function, we have the lyapunov is equal to half xe pxe xe transpose pxe plus 1 over gamma theta tilde. Theta tilde is this difference between these two. So this function, as I said, is function of the error and the error in parameters and the error in states, both between the two systems. So when we say v of 0 is equal to 0, our 0 here is 0, 0. 0 in the xe and 0 in theta tilde. Right? So this 0 is a vector. It has to be interpreted as a vector with all the errors that we have inside the system. So the function is positive, clear? It's 0 at 0 when both of them are 0. Otherwise it's not 0. And now, so it qualifies for a lyapunov function. Now I need to make sure that the derivative is negative. So when we take the derivative, v prime, so v prime is equal to half xe transpose prime multiplied by p multiplied by xe plus half xe transpose p xe prime, because p we said it's a symmetric constant, it's a matrix that is symmetric, positive definite. Plus we can add 2b just to make sure that we are not going to carry 2 everywhere. 1 over gamma multiplied by theta tilde prime multiplied by theta tilde. We are okay with this? Alright, so this will be equal to half multiplied by the derivative transpose. The derivative we have it there, so it's 6e transpose multiplied by a transpose plus.
Professor, theta here is a vector or just scalar?
Who?
Theta.
Theta for now is just a scalar.
Scalar.
Because if it's a
Okay,
vector,
zero
we need
over
to
K.
carry on also the dimensions. So we are going to assume we have only one input. But nothing stops us from generalizing it to more. If I generalize it to more, then I need to put transpose. Huh?
Okay.
And then I will have enough derivative with all the parameters that are in theta. Okay. We will have occasions to do that, but we will do them with the particular controller. So when we go to the general form of adaptive control, we are going to first study, for example, feedback linearization without adaptive. Then we convert feedback linearization to adaptive. Then we go to sliding mode, and then we convert sliding mode to adaptive. Then we go to backstepping, and we convert backstepping to adaptive. So we see each one of these controllers, and we convert them to So plus we have here B transpose multiply. In fact, since U it's just a scalar, we are going to keep it as it is. Tilde multiplied by U reference. So this is XE transpose prime multiplied by P multiplied by XE plus XE transpose multiplied by P multiplied by the same thing. So A times XE plus B tilde times U reference that you have here.
1/2.
One of us. Plus the last term, which is 1 over gamma multiplied by theta tilde prime multiplied by theta tilde. You agree with this? Alright, so I'm going to connect all these terms that we have here with the A together. So what we are going to have is half multiplied by XE transpose multiplied by A transpose multiplied by P plus P multiplied by A multiplied by XE. So I'm going to use this term with this term, this term with this term. So these two terms that have been used already. And this is what it will give you. Everybody agrees with that?
Why we didn't select just one? Because overall is scalar.
Why did not select one?
Yeah, for example, why just select XE dot transpose PXE without 1/2.
Well, it's just a scalar.
Yeah, so it's all scalar.
But it will appear later on in our calculations. We'll see how it works later. Plus half, and here I have B transpose multiplied by P, B transpose multiplied by P multiplied by XE, right? B transpose multiplied by theta tilde, right? Plus XE transpose multiplied by P multiplied by P multiplied by theta tilde, the whole thing multiplied by U reference. You agree with this?
Plus 1 over gamma.
Yeah, we did that. Yeah, plus 1 over gamma. But these terms are correct. Plus 1 over gamma multiplied by theta tilde prime multiplied by theta tilde. You agree with this?
Yes.
Alright. So now we are looking to one single input, huh? One single input. So we're going to look to these two things. This is 1 by n multiplied by n by n multiplied by n by 1. And theta tilde, I'm assuming it is 1 by 1. Huh? Everybody understands why? We have only one input, so beta transpose has n states, but it's only one column. So if I take the transpose, it becomes 1 times n, one row, many columns, n columns. This one P is n by n, same dimensions as A. The vector XE is n by 1, and then I have 1 by 1 here. So if you multiply these these three together, you will get 1 by 1. 1 by 1. Everybody is okay?
Okay.
Now I go to the next one here. XE transpose is again 1 by 1. This one is n by n. And the last one will be n by 1. So the multiplication for these will give me 1 by 1. So this is a scalar and this is a scalar. And this is the transpose of this. So they are both
The same scale.
the same scalar. And this is why we put here half. Just to remove the 2. But otherwise I will have it in my calculations later. Alright, so basically what we are saying that these terms are both equal. You can select any form of these and it's exactly the same term. The form that we are using here is B transpose P multiplied by XE. Right? So we are going to take basically this one. B transpose P multiplied by XE. Everybody is okay? Anybody has a question? Clear? So we do exactly the way we did it before the break. The question is how to make V prime negative. So to make it B prime negative, since this is a quadratic term, it may be sufficient to have
P.
A transpose P plus P times A
Negative.
give me something negative definite. Minus Q. So I'm going to say one way to do it is to have A transpose P plus P multiplied by A equal to minus Q, and Q is symmetric, positive definite. Huh?
Yes.
So this is one of the conditions. If I have this only on this part, it's not enough
We need to check
because
all
we
of
have
them.
this one here.
Yes.
So I'm going to select theta prime to make all this term zero. Right? I'm going to select all this to make this term zero. So I'm going to select 1 over gamma theta tilde prime times theta tilde
Equal.
plus B transpose P XE theta tilde equal to 0. We did exactly the same example before, huh? Exactly the same strategy. So this will imply that theta tilde prime is equal to minus gamma times B transpose times P times X.
Okay.
I think we missed your reference, huh? So your reference should be here. It's here. This is your reference. So this multiplied by 0. Now I need you to pay attention to what I'm going to say here. V prime is going to be negative if I use these two conditions, if I satisfy these two conditions. If V prime is negative and V is positive, then the value of V will converge to 0. And conversion to 0 means
The error.
the error is 0 on theta and XE is 0. But if XE is 0, this means that the derivative here is 0. And if the derivative here is 0, it means that this one converges to a constant.
I didn't get this part, please. Can you
Repeat this again?
the last one?
Right. This one you don't need to, you took it already,
Yes.
huh? So I'm going to write V again, back again. So V, we said it's equal to 1 over 2 x transpose Px plus 1 over gamma theta tilde square,
Okay.
right?
Yes.
If I use these two conditions, condition number 1 and condition number 2,
B prime is negative.
then V prime will be negative,
With positive.
which means that V will converge to 0.
Zero.
Try to converge to 0.
Okay.
If V will converge to 0, means that XE is 0, because this is quadratic, right? And theta tilde is 0.
Okay.
If XE is 0, it means that this theta tilde prime, the derivative of theta tilde, is equal to 0.
Okay, my mean theta is constant.
Which means that theta tilde is constant. The error will converge to a constant.
What
Right?
constant?
What you hope is that this constant is
Small.
0.
Small, so small.
If the initial condition is 0,
If the
it will
initial,
integrate. So we have plus C.
If
It
it's
depends on the initial condition.
it has to converge. It depends on the initial condition for this integral to continue, but it depends on this term because this term is exponential, right? So
If,
what?
if it's not close to zero, like theta when we find it, what we will do?
Exactly. What will you do? This is in fact my next question. So this is the reason why we should not only make sure that V prime is negative. We need to make sure that this one does not go to infinity. Because this one can converge to infinity, right? A big number, right? Infinity. And you will have V and this one negative. But this one will blow up. This one blowing up means
This
V
will
will
go.
blow up. So what you need to do, you need to make sure that your error converges faster to zero than this term go up to infinity. Everybody understand what I'm saying here?
Sir, but we said that theta prime will be equal to zero if V is equal to zero.
If V is equal to zero, theta prime is equal to zero. But what is this theta prime equal to zero? Means what?
Theta is
It means
constant.
the error is zero.
It means theta is constant. Theta tilde is constant. Not the error is zero.
Theta tilde what is? Theta means theta
Zero.
zero.
Theta star.
Means
Theta
Yeah,
tilde.
the desired
The error is constant. What you want is that the constant is zero. But maybe you are going to be
Bigger
convergent to
number.
any
Why
other.
is it constant? Why is it not zero? I don't get it. V is zero. Theta
The
tilde is zero.
derivative
The
is
derivative of constant is zero.
constant.
No, derivative is zero.
Means that you have minimum.
So we have V is equal to zero.
V will try to go to zero, but it's not zero. Right? Because this one will converge to constant, means that this one is not zero. XE will go to zero, but this one will be
Constant.
a constant. What you are trying to do is to have V go to zero, or be minimum at least, right? You are going to constant. But this equation is telling you that if XC is zero, or closer to zero, that's minimum, right? Closer to zero, then this derivative is also closer to zero, which means that it's closer to a constant. What is this constant?
We don't know.
I don't know. So my remark is here first. We need to make sure that this analysis is valid. Yani not only the derivative the derivative of V is negative, but you need to go back and check that this value of V is not going to blow up because of theta. So it means theta has to be
Close to zero.
finite, limited. And the other conclusion is that this theta will converge to anything, not necessarily your right value of theta. Do you understand what I'm saying here? So we started with theta equal to theta minus theta zero. The derivative of this is equal to a constant, means that we are going to converge to any value of theta zero plus something, not necessarily theta zero. So whatever you are going to converge to from value of theta, you should not take it as the value of the real value of theta zero. This is the conclusion. Ideally, you would like both of them to converge to zero in theta tilde, which means that this derivative will converge to zero when both of them are equal. Right? You converge to the right value of theta. But this is not guaranteed. You agree with this?
Yes.
So this is something that you need to pay attention to, and you need to always verify whenever you do something in adaptive control and you have this type of lyapunov function. You need, after proving that V prime is negative, go back to show that theta will not blow up. Could be contained. Could be finite.
We
Alright.
need to calculate it to show.
You need to make the analysis. Make sure that XE will converge to zero. There is only one equilibrium point in the area that is zero, and it goes at the rate that is controlled faster than the value of theta. This kind
A
of
lot.
So, to summarize, Doctor, we need to make sure that V prime is negative.
Yeah.
XE is converging to zero or converging
XE is
faster
faster than theta.
than theta is converging to infinity.
What? Not infinity, whatever constant it is.
This is all our conditions to make sure that the
Right.
system is stable. Yeah,
Exactly. Some have seen some work where just by proving that V prime is negative, we call the student or the author concludes that خلاص done. we are going to have the adaptive control working. This is
What if we use like a sliding mode?
same thing. Sliding mode is
Because
another
it's
story.
finite time.
Huh?
Sliding mode is finite time. It's not exponential.
Well, it depends on what you do with the sliding mode. Sliding mode, the reachability is finite.
Yeah. You reach the exponential. Okay.
Because sometimes you go and
Switch.
you rotate around the equilibrium point. You will never be able to convert the equilibrium. You slide, but you keep rotating.
So it's switching.
Yeah.
That's something.
But we will see sliding mode later on. What we do with the sliding mode, inshallah, and what are the reachability conditions that are explored. But everybody is okay with this? What I did up to now? The important thing is that what I have said, which is the analysis that we need to do after to make sure that this converges to find value. The second very important is that the value of theta converging is not the right value of theta. Don't take it as the right value. It could be the right value, but it's not necessarily the right value of theta. And don't expect theta to converge to theta 0. Can converge anywhere. Maybe closer to theta 0, maybe far, we don't know. The other thing is that the adaptation rule, it depends on the state. It does not depend on the output. You agree with this? Alright. So now this first condition, A transpose P plus P times A, we have seen before when we reviewed the lyapunov that if A is stable, then there exists P and Q such that this equation is verified.
Okay.
Otherwise, we need to make sure that
Hey.
find P and find Q that verify this condition. Alright? So now in order to make sure that both systems are equivalent, the state feedback and the input output are equivalent, we need to make an extra condition. We need to go here and say, how can we rewrite this term as function of the output? Right? So now we go back to our system. Our system was x prime equal to a times x plus b multiplied by u. Y is equal to c multiplied by x. The same thing for my reference model. AM or a multiplied by x plus theta 0 multiplied by b multiplied by u reference. And of course, ym has to be the same states. C multiplied by xm, the same C. And cannot compare two different C's. So the system is then this. It says, if I have my system and I'm able to find, if you are able to find P, such that P verifies the stability condition. This is stability conditions. Huh? It makes V prime negative, but it's stability conditions. And it verifies also that B transpose P equal to C. So basically, go back here. If I have P such that B transpose P is equal to C, then C multiplied by XE will be equal to Y minus Y. Right. So if I write Y minus YM here, it will be equal to C multiplied by XE. And then it becomes based on the output feedback. So the state feedback and the output feedback are equivalent. So this is the results here. It says, if you are able to find P that verifies these two conditions at the same time, then your state feedback adaptation rule is equivalent to your output feedback.
The second condition is also for the lyapunov.
Which one?
First, second condition, B transpose P equals to C.
It's coming from here. From this term. B transpose P is equal to C. If I make sure that B transpose P is equal to C, then this will be C times XE, which is the output error. So this theta tip will be based on output feedback, not based on state feedback. So this coming from lyapunov, and this is coming from lyapunov. Did I answer the question? I answered your question or not?
Because the first condition we have seen in the linear multivariable for the lyapunov theory, and mostly we saw the first condition in the papers and
This is for stability only.
yes. I'm asking about the second condition, that it is for the lyapunov stability or
No. This is the stability condition.
Okay.
And this additional condition is to make the output feedback, state feedback, state adaptation rule. Equivalent to output adaptation rule. Output adaptation rule means what? MIT rule. Because MIT is based on an output. Is it okay with that? It's clear now? So this condition, we added just, we don't need it. If somebody is asking me, design a lyapunov, not lyapunov, adaptive controller, and I don't care if it's state-based adaptation rule or total adaptation rule, they are equivalent, not equivalent, I don't care, but just design for me lyapunov, I will stop here. But if somebody tells me I would like when this will be equivalent to the MIT rule and the output based adaptation rule, then I will tell him I need to have B transpose P equal to C. So basically, when I run a lyapunov function in MATLAB, it's not only to find the Q or to by putting Q to find P, but also to make sure that
to check
this constraint is satisfied. And then at the time we are able to say what we did with the output feedback is equivalent to the state feedback. Is it clear what I said here?
Yes.
And the question is when this is possible. Right? So here we are going to enter in what we call the positive real transfer function passivity conditions. So going to go back. The question now is not only lyapunov finding P and Q, but it's only finding P such that it verifies this constraint that we added here. And the question that you need to answer is, when can we do this? When are we able to find P that verifies both? Is it clear what I said here?
Yes.
So in order to answer this question, we go to what you call positive real transfer functions. So we are talking about Kalman-Yakubovich lemma. It says here a rational transfer function G with real coefficient is positive real if the real part of G of S is positive or equal to 0 for real part of S positive or equal to 0. And the transfer function G is strictly positive real if G of S minus epsilon is positive real for some real epsilon positive. Right? What does it mean? So we go back to, maybe you can take an example and see how it works. So last time I used with you first order system with lyapunov, and I did not even talk about positive realness, and we will find them that they are exactly equivalent to the MIT rule. So if I take the transfer function 1 over S plus A, for example, this is my transfer function G. It's a rational transfer function, numerator, denominator.
Okay.
Now I'm going to take S and I'm going to assume S is equal to A plus Bj, so real part and imaginary part. And I'm going to assume that the real part of S, which is equal to A, is positive. Alright? So this is my assumption.
So
That,
it's unstable here or
no, I did not talk about stable and not stable.
We're not looking at that.
So I'm still talking about
Combination.
positive realness. We'll see after that it will be related to stability. So if I put S inside, not A, we have to change alpha maybe, alpha plus beta. Right? So I have alpha plus beta j plus A. This is my transfer function. If I replace S by this one.
Yes. Okay.
I need to compute real part of this transfer function. So I multiply by the conjugate both sides. So this will be equal to alpha plus A minus B times J divided by alpha plus A squared plus beta squared.
Okay.
You agree with this?
Yes.
Right? So this would be the real part of J will be equal to alpha plus A divided by alpha plus A squared plus
B.
beta squared.
Oh.
So this lemma is asking me to compare this real part to
Positive.
0. Is it positive or negative? So and the question is here, is this positive or equal to 0?
Based on the
Depends
values
on
of
the
alpha and A.
numerator.
Sorry?
And B. And beta.
It's based on the values of A and alpha.
Alpha, we took it positive already.
Depends on A.
On
A should be
Greater than alpha.
0.
Positive.
It could be
Because
negative.
Unless the
It could be,
absolute
yeah.
value less than
B.
alpha here. For real part of S positive, not a particular real part of S positive.
all the values of alpha.
All the values of alpha.
So
No
0
condition on alpha.
Yes, yes. So it should be positive. A should be.
So A should be positive. If A is negative, then there should be a value of alpha bigger than A that will make the system positive real, and this is not the positive real in this theorem. Everybody is clear about this?
This is for every alpha.
It's for every alpha. There's no
Every
condition
positive
alpha. No condition alpha. So we are saying here that this is positive or equal to 0 if A is positive
Or equal.
or equal to 0.
Or equal.
Everybody is okay with this? A positive or equal to 0 means this is stable.
Yeah.
Right? So it's related to stability. Everybody is okay with this?
Yes.
So this is exactly what this result is saying. Right? Now if I take the strict positive real part, the strict positive real part is assuming that S, we are using S minus epsilon. So we have alpha minus epsilon plus beta multiplied by J. Right? So this is my new S. And if I compute again the value of G, I will find it equal to 1 over alpha minus epsilon plus beta times J plus A. The real part of this G is equal to alpha minus epsilon plus A. The whole thing divided by alpha minus epsilon plus A, the whole thing squared plus beta squared. So for this function, in order to be strictly positive real, it has to be already positive real. So we are going to assume
A is superior.
A is already positive. Right? So the system is already positive. Now when it will be strictly positive real? It says there is a value of epsilon such that this real part of the system is positive. So if I take epsilon equal to A, since alpha is positive, the whole thing will be positive. There is a value of epsilon and the system is strictly positive real. So to be strictly positive real, it has to be
A.
positive real first, so A positive, based on our analysis here. And then after that,
Epsilon.
if I take epsilon bigger than A, bigger or equal to A,
No, smaller or equal.
smaller or equal to A, the value of A is enough, then the system will be strictly positive. Everybody's okay with this?
Yeah.
So what do you mean by the positive real or strictly positive real?
Positive real, that's the definition. A function of the system is positive real, transfer function is positive real. If I select S, the real S, such that the real part of S is positive, I plug it in the transfer function, I will find that the real part of this function, this transfer function is positive. This is positive real.
Yes.
That's the definition. Strictly positive real means that if I put an epsilon, I will find that the function is
Still.
bigger than 0 with an epsilon. I move the axis if you will. This is just a shift of the axis, of the 0 axis. So there is a value of epsilon. If I shift it a little bit, I will be able to have the function, the positive realness, but at different axes.
Can we see that as a stability? Like if we shift the system a little bit.
It's related to stability, but it's not stability. Okay. Okay.
Does that mean that A is strictly superior to 0? Does it translate to A is strictly superior to 0?
To be in the positive
Strictly positive.
to be strictly to be positive, A has to be.
To be strictly positive real, I need to say A is strictly superior to 0.
Listen, I would like you to do this for me. Take G of S equal 1 over S and tell me what you conclude. Do it. To complete it, tell me.
If A is 0, in this case A is 0, and if A is 0, based on our calculation here, A has to be 0. And if A is strictly positive, then we have our epsilon.
And 0
It has to be greater than 0. That's what you call the A, it has to be 0.
The condition says that
وزيرو يفاز
the epsilon has to be strictly positive. Huh?
Yes, but in this case it's
So it doesn't work. It's not strictly positive.
Excellent. Okay, so there is no positive epsilon value different from 0 that makes 1 over S strictly positive.
Yeah.
So 1 over S
should be minus.
is positive real, but it's not strictly
strictly
positive.
Yeah, but I'm asking, whatever value of A is strictly superior to 0, will make the system strictly positive.
Yes, this is what it says here.
Yeah. So
Any
the
value.
condition will become A strictly positive, strictly superior to 0, not
Equal.
superior or equal. It's going to be strictly superior to 0.
For this one you mean. This condition is only for positive realness.
No,
And for me, I go to strictly positive, A
yeah,
has to
it
be
will
strictly
be
positive.
strictly superior to 0. That's all. Yeah.
Everybody is okay with this? We agree?
Yes, sir.
Any other question? All right. This is the Kalman-Yakubovich lemma. It says the following. It says that, and you have to pay attention to this because our starting point is the state space model. It says the time invariant linear system. Time invariant to make sure that the coefficients are real. Right? Coefficients are real. They are not function of time. See here what we have. In the lemma it says the function has real coefficient. We need to have constant parameters. This is the state space of the system. The system has to be completely controllable and completely observable.
To go to the transfer.
The transfer function g of s is equal c of si times minus a. We have seen this before.
Yes.
So what's the link between this transfer function and this condition of controllable and completely observable?
If it's not completely controllable and observable,
We can go to
can't
transfer
find
function.
this,
We can?
we can't have g of s equals.
We
to
can.
C.
Why we can?
It will be inversible.
We are always able to find the transfer function of the system. So
We said if the system is controllable or observable, we can go to the transfer function.
we can't, Willa, we can.
We can, if it's controllable and observable.
We
We
cannot.
can go.
I said that?
Well, the first time,
And I did not say that. If I said that, I was sleeping.
For this system, we need to have the system completely observable. Otherwise, we don't have the state's error.
Right, maybe from this point of view, but for this one here, for this level, completely controllable and completely observable. Means what?
You can go to transfer function.
The value of s.
First of all, are we able to find transfer function for any system?
No, if it's not controllable, we
It's
can.
not controllable.
We can transfer function.
I did not say that. Don't get out of this and say that the same. You said if it's not controllable, we are not able to find
You
it.
can't find the determinant of A. You can't find the determinant of A.
We can always find the determinant of A. We talked about at the beginning of the class that the system is decomposed, Kalman decomposition in 4 different
Yes.
parts. Completely controllable, completely observable, or completely controllable, non-observable, or non-controllable but observable, or not controllable,
No,
not
observable.
observable. But the transfer function represents
controllable and observable.
The controllable and observable part. So when we say here this G of S equal to SA minus A times B, the system has to be completely controllable and completely observable, means that this is the minimum realization of the transfer function. They say something that tricks the bell. Minimum representation means there is no state that will disappear from the transfer function. Because the transfer function represents the controllable and the observable part, and the system is completely controllable, completely observable. So all the states are already captured in the transfer function. Nothing disappears.
Okay.
If the system is not controllable or not observable, we can still find the transfer function, right? But this transfer function will not represent all the states. Some of the states, so it's not a minimum representation.
Okay.
System has, in its representation, has 4 parts according to Kalman: completely controllable, completely observable, controllable but non-observable, observable but not controllable, and not controllable, not observable. If we take a system that is not controllable, not observable, has non-controllable, non-observable states, and you will find the transfer function of the system,
It's not complete.
these states you will not see them there. They will not appear. You are losing information from the system. So the transfer function represents the controllable and observable part. Everybody understood why we have the condition controllable and observable. Means, if I take this transfer function, I try to find the state space, I will find exactly the same thing. And if I take the state space and I go to the transfer function, I will find the same thing. It's a minimum representation. Is it clear what I said here? Alright, so if I take this system, which is completely controllable, controllably observable, and I compute the transfer function, and I find that the transfer function is strictly positive real, then it means there is a P, such that A transpose P plus PA equal to minus Q, and B transpose P is equal to C. And if I have a system in transfer function, system with a state space, and I'm able to find a P that verifies the stability condition and B transpose P equal to C, it means if I compute the transfer function, it will be strictly positive real. So it's an if and only if condition, right? Both conditions. Make sense for you? Right? So one way to do it for us to see if there is a P or there is no P is to compute the transfer function of a system, and then you show that the transfer function is strictly positive real. But before computing the transfer,
We need to check the
we
control
need to
bit.
check the
Yeah,
control.
absolutely.
Otherwise, we have to go and say the controllable part and the observable part of the system is this. And then we would like to see if this part working with the controllable part and observable part only is enough.
So,
When
for the P, we can find it from the last equation.
We can
Find it.
we can find from last question. No.
Yeah. We have B, we have C.
So how can you find it? B transpose P equal to C. This is a
So the
vector and this
inverse-
is a vector, huh?
So the inverse of
Hey, the
Can we
inverse
not
is
calculate it with our no MATLAB?
we cannot calculate. This is a constraint for this.
yes, you need
Yeah,
to.
I mean, if we can find P from the one below, we replace it in the one above, and we check if
there exists a Q.
You can.
can do it backwards.
Or you put
To be 100% sure that the condition below is.
and is there one P that will do this?
I think there's
Is there
multiple.
one P?
Yeah,
Yeah,
yeah.
If you use the
no, it looks
pseudo
like there's
inverse
one
for
P that
B,
verifies that
pseudo inverse
condition.
for C,
Ah.
there's two.
Sorry?
At least two.
Why? There is one B, one C. So there should be one P.
B C vectors. لازم تاخذ معاها pseudo inverse.
The pseudo inverse.
Ah, okay.
So إذا if you work with the pseudo inverse of C, you get one. If you work with the pseudo inverse of B, you get another one.
So, okay. For us, we will consider it as a constraint for the stability. So the stability condition is this, and then not any P. The P has also to satisfy B transpose P equal to C. P We are okay with this? So what are we trying to do after basically, just to summarize?
Output adaptation.
To the adaptation, this is our question. Is
Yeah.
these two equivalent? Right? And this is what we are working on. Are
Why
these
do we need them to be equivalent, sir?
Why we are, because if you are able to make sure that they're equivalent, then the question of stability of MIT rule, do you remember the question of
Yeah.
stability of MIT rule? We had an issue when we tried to prove the stability of the MIT rule. We had to make a lot of assumptions.
Yes.
And we said that it was difficult for us to make it, but with this,
We
I
can
can
use
go
this
back and
directly.
I can show that it's stable. Okay, so I can use the approach. All right, so this is the model reference adaptive systems using lyapunov rule. Consider the problem of adapting the feed-forward gain. We are still talking only about feed-forward gain, which is the simplest issue that we are looking at. Assume that the transfer function g is strictly positive real, then the parameter adjustment rule, derivative of theta with respect to time equal to minus gamma uc multiplied by e, where gamma is positive, will make the output error in equation 5 go to 0. So the system will be stable, will converge to 0. Huh? So if you are able to, if you have a state space model and you verify it's controllable and observable, and you compute its transfer function, and you see that the transfer function is strictly positive real, then you can directly put the rule with theta. This is the rule for adaptation. For the feed-forward gain, but I'll still talk about the feed-forward gain.
Is it the same for the state adaptation rule? Can we just put the law directly? The adaptation law.
For the state adaptation, yeah, with lyapunov, we have to go, of course, with lyapunov, but this is.
It's really the same.
So this is our design procedure. First of all, we are going to find the control loss. So we assume the steps of our controller. We derive the error equation. We find the lyapunov function. Then we construct the parameter adjustment rule from the lyapunov function. Remember, lyapunov function, there is no rule. Lyapunov function, it's only by experience. After that, we can look to the adjustment rule, and we make sure that this guarantees that the error goes to 0. We cannot assert that the parameter converge to their exact values. This is what we concluded from the first
No.
result. It can converge to anything. هذا I don't understand. كتبتها وأنا نايم شكلي.
Maybe like the value of the parameters.
The value parameters are similar to those of the adaptation rules. Sorry, the adaptation rules are similar to the MIT rule. However, one of them is in state space and the other one is in output feedback. And yes, we have this condition. Exactly. So this first question of MIT versus lyapunov, we are able to answer it for the feed forward using this table. And this can allow us to prove the stability of the system or the convergence to the error to 0.
So, if you want to do the state adaptation rule, is there a way to prove that the error there will go to 0?
Definitely. Theta 10?
Yeah. You said that we want to
We
make sure
cannot
that
converge.
the lyapunov is not going to go up.
The error goes to 0. The error, not the parameter, goes to 0.
The error, yes.
The error means exceed.
Yeah, I mean,
Yeah.
how is there a way how to prove that?
Is there another way?
Is there a way to prove that? How to prove that
Analysis.
analysis?
We have to show that in the domain of definition of this lyapunov function that we selected, there's only one equilibrium point where the v is equal to 0 and v prime is equal to 0. If there is only one equilibrium point, then we can use what we call LaSalle theorem. Who did nonlinear control? Nonlinear control, course 517. Anybody did nonlinear? You have seen LaSalle theorem? LaSalle
Yeah.
Huh?
Did nonlinear form haven't seen that.
So,
They're not sure, yeah.
Yeah.
we're not sure. You have seen Lassalle theorem?
Theory about Lyapunov or
Lassalle theorem.
لا هي تكنيس
Lassalle theorem, basically Lassalle says if the Lyapunov function, if you define the Lyapunov function, the Lyapunov function derivative is negative, then and there is only one equilibrium point, then your error will go to this equilibrium point. And there is a proof for that. There is a theorem for that. Alright? In fact, Lassalle he looks to the integral of the function, so we go back here and then take the integral. If I take the integral of this function here, then the integral of this function, I can prove that it will go to 0, means that this error will go to 0. So this is this. Alright, stability system. So the first question that we put as a target, we already answered up to now. Now we would like to look to the stability, and then after that, come back and link both together. Stability versus like what your friend was talking about, stability and the adaptation for the other together. So there is a difference between state space versus input-output modes in terms of analysis, and in terms of linear versus nonlinear dynamic. And then for us, what we would like to see what this was not our class before Ramadan?
لا it's our class before Ramadan.
It's our class.
It's our class. 27.
The course starts at 5:20.
5:20.
5:30. What's the niveau? بيت مونيكا.
طيب اوكي. I think I'm becoming very old. This was not our class before.
Our class.
What? 130. طيب مش تسمعين انتم وانتم
This was our class.
The other one.
طيب يلا في كلاس هنا.
We still have just later.
اللي هم مش الكلاس الثاني نفس الكلاس.
We still have just later.
ماسكين بالكلاس.
We almost finished.
We will stop at this level today, inshallah. So I repeat, for Wednesday there is no class, Monday there is no class, midterm on Thursday, after Maghrib we agree?
yes.
After Maghrib? After Maghrib. And then we will plan for makeup classes for those